Alright guys, welcome back. So we're going to be talking about blood flow specifically through the heart. Here's a nice picture of the heart and it really kind of shows the blood flow, but let's break this down. So the superior vena cava is taking deoxygenated blood from the upper body and the inferior vena cava is taking deoxygenated blood from the lower body. And all this is draining right here into that right atria. This right atria is going to let the blood pool in here and then it's going to contract and it's going to push blood through this tricuspid valve. And this is really just showing you that blown up. You can see a nice good view of that tricuspid valve. So the blood can only flow one way. So it can flow right here into this right ventricle, but it cannot flow back. If it tries to flow back, this valve will shut and no blood flow. Now what's going to happen is this right ventricle is going to contract and it's going to push the blood through that pulmonic valve. That's that pulmonic valve right there. Once again, the blood can go out this way, tries to go back, that valve's going to shut nice and tight, no go. Well, the blood is going to go through those pulmonary arteries to the pulmonary capillaries. Blow those up a little bit bigger so you can see those pulmonary arteries right there. So here's the pulmonary artery. We're taking deoxygenated blood to the capillary right here. We're dropping carbon dioxide from our blood off into the air. We're sucking oxygen from the air and putting it into the blood. This vein, you see this is an oxygenated vein. Why? Because we sucked oxygen from the air and put it into the blood. And this is just really blowing up this exchange right here. So we have deoxygenated blood coming in and it's leaving as oxygenated. And so we got the pulmonary veins taking blood back to the heart. So the pulmonary veins are taking oxygenated blood into this left atria, both from the lung and from the right lung. And so the right lungs are going to have the right pulmonary arteries and the left lungs are going to have the left pulmonary arteries. Now we've blown up right here this left atria. And so this left atria is going to collect blood. And then what's going to happen is the blood is going to flow into this left ventricle. And to get that extra bit of blood flow, it's going to squeeze and push that little bit last bit of blood in here. And now the blood will want to flow back, but it can't because this valve will shut. No blood flow backward. So now that blood is in that left ventricle is going to contract, shut the bicuspid valve, also known as the mitral valve. Pressure is going to go up and up and up, and it's going to open up this aortic valve, and blood is going to go into the aorta. And this is a good look at the bicuspid, also known as the mitral valve. A couple of things about the bicuspid leaf. How many wheels are on a bicycle? 2. How many leaflets does the bicuspid valve have? 2. Alright, this is the semilunar valve. If you look at the aortic valve or the semilunar valve just right, it looks like half moon. So some overview on a couple of things. This chamber right here is called the atria, as is this one, right? Right atria, left atria. The two atria are going to squeeze at the same time. So squeeze, 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 blood's moving into the right ventricle. Squeeze, 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 blood's moving to the left ventricle. And that's happening at the same time. Now these bottom two chambers are called ventricles. And so the right ventricle is going to squeeze at the same time as the left ventricle. And so we're going to squeeze, 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 move the blood through the pulmonic arteries. Squeeze, 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 move the blood through the aorta and the systemic arteries. This is going to happen at the same time. So the way the heart is designed is that while the atria is contracting, the ventricle is relaxing. Why? Because if the atria were to contract at the same time as the ventricle, right, the atria is going to try to move blood into the ventricle, but if the ventricle were to be contracting, it's going to keep this valve shut. And because that valve shut, I'm not moving any blood in here. The other thing that's going to happen is when the ventricle contracts, the atria relaxes. Why? Because if this atria is contracting, we already showed that we're not getting the blood flow moving, right? But if it's not relaxed, blood cannot pour into this atria. And so the way the heart's set up is that while the ventricle is contracting, the atria is filling with blood because it's relaxed, right? And then once that ventricle relaxes, the atria can move the blood that it's been pulling in it into that ventricle. And so this can very quickly pump, 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 pump. Why? At rest, your heart's pumping blood every single second. 60 beats per minute. That's a slow heart rate. You're running on the treadmill. You're really moving it. Your heart could be pumping up to 4 times a second. So this thing has to be ready to move blood the second this ventricle relaxes. And so that is why this atria has to fill up with blood, and in order to do that, it has to be relaxed while the ventricle is contracted. So the next thing we have is the septum. And here's your septum right here. Your septum is going to separate the right and left sides of the heart. Why do we need a septum? Well, I spent a whole lot of energy getting blood from the body, pumping it out to the lungs, taking blood from the lungs, getting it ready to be pumped out to the body. If this septum didn't exist, this blood could end up going back to the lungs as oxygenated. Why am I pumping blood that already has oxygen in it to the lungs? That's crazy, right? There's no point in that. And so now I'm having to do a lot more work as I keep pumping the same blood back to the lungs without letting it go to the body. So the septum is going to stop that from happening. The other thing the septum is going to do is I got this deoxygenated blood coming from the body. I don't want it going to the body, right? Why does my body need deoxygenated blood? That's crazy. It doesn't. And so that septum is going to stop that mixing from it. All right. So if we look at our heart, particularly the right ventricular wall, you can see this is a lot thinner than the left ventricular wall. So why is the left ventricular wall so much thicker than the right? Well, it's not because the right isn't pumping out as much blood. If I pump out 5 liters per minute over here, that means the left side of the heart is getting 5 liters per minute of blood flow. And I cannot pump out more blood than what I'm getting. So they're pumping out the same amount of blood. So why is it so much harder to pump out the same amount of blood on the right than on the left? Well, the right side of the heart has a blood pressure of 25/8. And that's the blood pressure in the pulmonic arteries up here, 25/8. Well, what's the blood pressure in our body? Well, a normal blood pressure is 120/80. And so that blood pressure is a lot higher. And what that means is the left side of the heart has to be a lot stronger to pump the blood